Good morning to the class. My apologies, I had my mic muted when I started talking. Before we continue with this lecture, the lecture is being recorded, and I'd just like to check. Do you see uh, the book, the green book on your screen? The green
Yes, sir.
PDF. Okay, thank you for that. Right, the lecture is being recorded. I have stopped the transcription. Okay, let's proceed with this lecture. There's two things I want to do in this lecture. Uh, Initially, my intention was to do a tutorial on the Hardy cross method, but that only requires a single period, and Monday was a public holiday, so we did not have a lecture then. So what I'm going to do, I'll do the Hardy cross tutorial next week Monday's lecture. Uh, you do have a test also Monday morning, but we have a lecture at 11 o'clock, so I'll just briefly go through that Hardy cross example with you on Monday after the test. In today's lecture, there's two things to cover. The first is a correction to one of the previous tutorials I had given to you, and thanks to one of the students who alerted me to that error in it. So I will upload these documents immediately after the lecture. I'll load it onto Moodle, so you will have access to it. And then the second thing I want to cover in this lecture is the section on valves and fittings in a reticulation network. That, there's two documents that cover that so the section on valves and fittings. The first one is the CSR document, and that's on. It starts off, I think, on page 26 of that document. You'll see there. It's a short section. It gives you from a design perspective what you need to know about valves and fittings. And then there's a more extensive discussion of the topic in this particular book, which I'll also upload the link for you onto Moodle. It's available from the Water Research Commission, and you can download it for free and read the relevant section on that. So the chapter on valves and fittings in this particular document, I think it's page 77 of the book, is the section that we're going to cover. So that's chapter 7, this entire chapter. You can see there, page 77. Right, so I'm going to go to that. So before we proceed with that, just to the tutorial. Okay, one more thing before we proceed with the lecture. Your test is on Monday, Monday morning, 8 o'clock. And it will cover the scope of the test is all the work that we've done prior to the Hardy cross method. Right, so everything that we've covered before the Hardy cross method. So yeah, that's all. That describes it all to you. The work that you need to know for test one. Test one, I did send out an email yesterday. In this regard, it will be online. I believe the dean of students is still facilitating and arranging your access cards for you to come to campus. And some of you might not have it. Personally, I prefer that you have written it on campus, but uh, some of you might have, the time is short to obtain those cards, so that's why I've changed the test to an online test. Right. But please, you need to get those access cards, do whatever is necessary to get those access cards to campus, because your test two and the examination for this subject will definitely be done on campus. It will not be online assessment. So it's only this as a temporary measure, the test one, that's going to be an online assessment. Okay, so with regard to the tutorial, there was this, you may be familiar with that. I did go through this tutorial with you, or issue it to you. In fact, I went through it quite quickly and told you that you must study it yourself. Uh, uh, it's all the answers are all written there. And one of the students pointed out or raised a query about it. Uh, this was the solution that was given there, and there were two pipelines you had to design. The question asked you to design, I think, pipeline CB. Sorry, this coming. Select a suitable. Yeah, okay. This I just want to go through this here. Let's get my highlighter. Right. You have to select a suitable pipe size for pipelines CB BA and BD. Now, in the solution that that I've given you, I've done it for CB and BA, and I left it to you to do BD. You can still do BD. It will be similar to the procedure that's followed in BA. Right now, CB is fine. The design of that is fine. In BA, one of you created with me the peak factor for that pipeline, and I have had a look at it, and there is an error in the uh, peak factor that's given in the solution. And the reason why that error has occurred is, and something that maybe you should be wary of also and take cognizance of, the table for the peak factor is the table uses figure 9.11, and it says here, sorry, this is the table in. Sorry, okay. The table I had used was the one for undeveloped or developing areas, right? So I'd used the wrong, I'd read off the value for for the pipeline, the second pipeline, from the wrong table. Right, so this is something to be wary of, that you don't also make that same mistake. In the CSR guidelines, if you go to the CSR guidelines, there's these guidelines here, you'll come across two separate tables for the demand. Let me just go back here. The correct one to have used was this table here that you just had a look now. It says the developed areas right at the bottom. And there's another table a few pages before that. That's this one here. It says for low cost housing. So it looks similar, but the values you'll interpolate will be different. So I had used the wrong table for that. Okay, coming back to that particular one. Right, so this was the memo that was given. The pipeline CB, there's no problem with that. In pipeline BA, the error occurs here. It says here the peak factor is 7.3. It cannot be a lower peak factor than the first pipeline CB, because pipeline CB is serving more units then or the equivalent urban is, if you look at it, about 168, whereas for pipeline BA, the equivalent urban is 85. The fewer the urban, obviously the larger will be the peak factor. So obviously there was an error in that, and I have gone ahead and corrected that. It does not make much difference in the final design. You will still end up with the same pipe size. What will happen is you'll get a larger uh, head loss in the pipeline, but you'll still the final residual pressure will still be well above 24, so it's fine with that. The corrected solution, and that's what I'll put up after this lecture. I'll put it up for you onto Moodle. So this is the same tutorial, and the corrected tutorial, you'll see. I just need to clear my throat. Sorry about that. In this one here, you'll see the corrected peak factor of 10 has been applied there. That peak factor has been obtained from figure 9.11, which is for developed areas. You can see not for low cost housing. That's how it is for developed areas. So this time I read it from the correct graph. And the calculations is all the values thereafter where the peak factor is applied, those values will change. So the actual the Q, capital Q, the design flow, we have the peak factor, so those values will change. But the so the numbers after that all change in the equation, but you will still require the same diameter pipe at the end. You can try it out. You can try using a smaller diameter pipe. So, for example, in the question, you were given pipe sizes 100 NB, and then you're given an 80 NB. You'll see an 80 NB pipe will not work. So you'll still the smallest pipe size that still works is a 100 NB in this particular design. Right. So go through it. You see now this time the head loss is about 24 meters between those two, between pipeline A and B, and the final residual pressure of about 60 meters, which is still well above the minimal residual pressure of 24 meters. So a 100 diameter pipe is still quite adequate in this case over here. Right, so this to alert you to that, that there was an error in that tutorial, and I will post the corrected tutorial for you onto Moodle. Okay, let's move on to the discussion on valves and fittings in pipelines. Now, when it comes to valves and fittings in the pipeline, so I just want to go down to the relevant section. In the CSIR guidelines, please read through these guidelines. They talk to you from the perspective of the actual design as a design engineer. So they, in that language, they're written. So they give you guidance in terms of the actual design when you're designing a network. It's just 1.5 pages or so of that you need to read, so please do read it. You'll see that they discuss isolating valves and air valves and then scour valves. You see, those are the three scour valves. Scour valves, anti-vacuum valves, and brake pressure devices. Uh, these are the main fittings that are discussed in this particular section. The section on surge control valves I will discuss when we discuss water hammer. So you'll find mention of a surge control valve there, and valve chambers and marker posts. These are just structures that go around or with a valve when you install a valve in a system. That's all there is in the CSR guidelines. Please read through these things, and they explain the purpose for these valves and the need for these valves. You'll find a more extensive discussion on this topic in the Water Research Commission document. And you'll see chapter 7 of that particular document. And here they also have some pictures which might help some of you, to visualize what's going on. So I'm going to use this document. They also give you the reasons why we put in the valves. So why? Firstly, in any water distribution system, you will require a large range of fittings and accessories. Right. So that's the basic thing to remember. Let me just get my highlighter. So water distribution systems, they require a large range of fittings and accessories. And the purpose behind them is to link pipes and to facilitate operation and maintenance. So it'll be one of those reasons why you're going to have these valves in the system. You can read through the rest of it. The types of valves that are used in a distribution system, that's important to know what types of valves that are used in distribution systems. Isolation valves, the name says it all. It means you want to isolate a section of the network. And there'll be the reason why you want to isolate a section of the network would be usually to carry out some repairs or maintenance on the pipeline. So that's why you would to cut off the water supply to a portion of the network. So those are and there are different types of valves that you could use to achieve that. Right, so you'll find the discussion below on isolation valves. Air valves, the name again says it. It's got to do with air in the pipeline. They serve. You either want to introduce air into the pipeline, or you want to remove air from the pipeline. It may seem contradictory, but there are times when you want to. So when you're introducing air into the pipeline, it's then referred to as an anti-vacuum valve or a vacuum release valve. And when you're removing air from the system, then we refer to it as an air valve, and it serves a dual purpose. There are valves that just serve a single purpose. You can get just a vacuum release valve or just an air release valve. But most valves commercially available, good quality valves, like Ventomat or the valves like that. And there are many other makes. I'm not choosing one make over the other. There are actually many other makes of valves. They usually will come as air release valves and vacuum release valves. So they serve a dual purpose there. Right. And I'll talk about it now as we go through just the discussion of what these valves do. Scour valves are used to drain a pipeline. So if you want to empty out the water from a pipeline for whatever reason, you may be doing some maintenance work on the pipeline, you may be doing repairs on the pipeline, and you need to empty it out. So I think my signal, something went wrong. Why was it my computer making that sound? Okay, I think this is back again. Okay, so scour valves, they serve the purpose to drain the pipeline system And you can see now that these valves work in tandem. If you're going to drain a full pipeline, uh, you then will there'll be no you're taking out the water in it, but if you do not fill the space with air, you will then develop a vacuum in the pipeline, and your pipe may collapse. If you have a plastic pipe or a thin wall pipe, it will then because you now have a vacuum in it, and you got soil pressure on the outside, so the pipe may could quite easily collapse or deform or get damaged like that. So you can see that, okay, if you have a scour valve in it, then surely you're going to need to put a vacuum release valve in your pipeline system. The second purpose, or another purpose for scour valves, is to remove dirt and grit and sand or guns, whatever that may have accumulated in your pipeline. You don't want sand and things to normally this appear in your pipeline because they would cause contamination, and then you got health hazards in that regard. The water potable water uh, is usually chlorinated water from a reservoir, so it's usually free of bacteria and things and contaminants. And if you're going to have start introducing sand and things into your pipeline, you're then introducing contaminants, and that could be a health hazard. So, how would that sand or something come in? Usually, when you have a burst pipeline or a cracked pipeline, you may have sand or whatever that may come in. They may replace a section of the pipeline, and you may have dirt and grit that may come into the pipeline. So after that repair, they would scour the pipeline. So they just waste a certain volume of water, so that the water that's now remains in the pipeline is potable drinking water and clean and free of contaminants. Non-return and check valves, these are to control the direction of flow in a network, in a particular pipeline. So if you only want the flow in a particular pipeline to be in a certain direction and you don't want a reversal to occur, that's when we would put a non-return valve, or what we refer to as check valves. And then control valves, there are various types of control valves. Uh, you get you may want to control the pressure in the pipeline. You may so you can regulate the pressure. You can keep it within a certain range in the pipeline. So these are specialized valves, very expensive valves, but they serve a very specialized purpose. So control valves, you could control, for example, the amount of flow in a pipeline. You could control the pressure. You could control. They sometimes used in at a reservoir, where instead of using a float valve, like what you have in your toilet system, you sometimes have a control valve that controls the level of water in the reservoir. Right, so it's in other words, it's by controlling the pressure within a certain head, you can control the amount of water in that reservoir and things like that. So these valves, control valves, will not necessarily be in every distribution network. Right? So control valves, non-return valves, and check valves, they are will be used in special situations. But the first three, isolation valves, air valves, and scour valves, these are common, and in most networks you will find the first three valves. Okay, so if you read to that, the discussion that you have here in this document for isolation valves, you can see isolation valves are used to close off or shut off flow, and they prevent any flow in the pipeline. So, like I said, the name says it all. Uh, you may want to shut down a section of the pipe for repairs or to isolate one particular supply zone from another, things like that. Right? So read through this. It's pointless me reading it over the lecture. You can actually read through that. The types of valves that are used are typically a gate valve. Now, a gate valve is a particular type of valve. It has like a big bottle at the bottom. It's a gate that when you turn the spindle, the spindle is like the handle of the valve. When you turn the spindle, this gate will lift up, and you can turn it in the opposite direction, and the gate closes and shuts off the valve like that. So that's just one type of valve. You get other types of valves that we call them butterfly valves. Uh, Gate valves are expensive, but butterfly valves are much smaller as compared to gate valves and more cheaper than gate valves. Uh, the thing is, well, with gate valves is that you can open, they generally will open slowly. You can control the opening of that valve, whereas with a butterfly valve, it's almost like just a 90-degree turn of of the spindle, and it'll be either full open or full closed. And I'll talk about it just now about actually opening and closing a valve. That's so they usually installed near at junctions in a pipe network, so where one pipe tees off from another pipe, and then you want to control that. The intervals also that are spoken about, you'll see 1 to 2 kilometers on transmission lines. You wouldn't want to have very long pipelines with just one valve on them, because then when you need to shut off, you will shut off a large area. The water will be cut off to a very large area. So usually the rule of thumb is about 1 to 2 kilometers, but again that depends on the design situation and net what funds are available for that particular network. The positions of it you can read. Usually you will have a marker. Uh, you have this concrete post or something that you'd put or some painting on the road to identify the position of these valves, because they're underground, so you will not see them. So that's why you need markers like that. Uh, the way these valves operate, I strongly suggest go on the internet and just type in gate valve picture, and you'll see a picture of it, or gate valve cross section, and you'll see a picture of that, and then you'll visualize how these valves work and what they actually do. Right? So the important thing when it comes to valves, whether it's for isolation valves, uh, the person who's operating that valve must be appropriately trained to do that. Now, it may sound like it's not as simple as just opening or closing a tap in your house. Or put it this way, it is as simple as just almost as simple as opening and closing a tap in your house, but you need a little bit more. You need to know a little bit more than than opening and closing a tap at home. And the reason behind it is that they should be opened and closed slowly. That's the important time. And you see, they give a time also about 10 minutes to open a valve. And that's a fairly long time just to open one valve. So imagine you're opening a tap at home, and it takes you 10 minutes to open that valve. To open that tap. So it's a fairly long time. Now, there's a good reason why these valves must be opened and closed slowly. uh, if the pipe for the pipeline is empty, right, there's no water inside, and you just suddenly open this valve full, so you get this wave of water rushing in. It has a momentum in it, and when it reaches the full point, it's like stopping a train dead. A moving train is like stopping it dead. We'll cover this when we do the section on water hammer. So you'll get water hammer in the pipeline, and that water hammer is strong enough to actually burst the pipeline if you open the pipeline suddenly. Right? The momentum of that flow of water in the pipeline, the water will have a very high momentum, and and suddenly when the pipe reaches its full position, when it's full, that momentum has to be released, and then the pipe wall will have to expand to take up that momentum of that moving water. You have to. It's like trying to stop a car dead. It's like knocking into a tree. It's something like that that will happen in the pipeline, and usually the pipeline will burst. So and it's common. And those of you that live in Itigwini, you often find that you have a burst pipeline on the road somewhere, and you get somebody, they come in to repair the pipeline, and they'll do the repair. And if they're not trained in opening once they've done the repairs, they will then open up the valve so that everyone can get water again. And if the person doing that is not trained, you'll see 2 or 3 days later, you'll have to call them out again, because there'll be more burst sections on that pipeline. And the reason why you have this problem of more burst sections is because there was water hammer in the pipeline when they open that valve. Right? So, an important aspect to note uh, in a reticulation network is the opening and closing of those valves. Uh, this is this particular book is about operating and maintenance, so it's not actually from the design perspective, but for you to design, you need to know how they operate and maintain the network. So you'll find the discussions here will center around all operating those valves over there. Another important aspect is about do not throttle the flow, so don't just open. Okay, having said that, this is referring to under normal circumstances, right? That you should not throttle the flow under normal operating conditions. But when you're filling the pipeline, that's when you're going to open it very slightly, the pipe very slowly, so you will then throttle the flow. This coming back, I'll talk about it also when we do a water hammer. Uh, if you want to know why these valves must, if you personally experience it, or why you should not open a valve suddenly full. Those of you that have a single lever tap in your at your home or in your shower or bathroom, if you have one of those the modern taps, the single lever taps, and you can literally in a fraction of a second open it full and close it. So if the tap is open full, the tap is open full at your house, and shut it close fast, and you'll actually hear a loud knocking sound. Right? And that's the water hammer. That's what's happening. You get that surge. If you ask somebody to do it and you stand outside on the pipe, you will feel that pipe move. You'll actually feel the vibration. You'll feel the knock on the pipe. Right, so that's just from a practical point of view. Please don't do this. Do it once or twice, or you might end up with a leak at your house. Right? But this something if you want to actually see or personally experience the effect of closing a valve or opening a valve suddenly like that. Right. Uh, so that's the isolation valves. That speaks about it. The important thing about opening and closing, the distances and where you actually use it, and the purpose of those valves. When it comes to air valves, you can want to control the. You just notice it says the control of flow into and out of the system. Right? Into the system, it's when you're carrying out maintenance and you're emptying the pipe out. Well, then you need to replace the water with air when you're emptying it out. So then you would want. That's when these valves would also work, and then it's referred to as a vacuum release valve. That you'd introduce air in the system. Under normal operating conditions, if you have air in a pipeline, it can throttle the flow. You may get air trapped at a high point in the pipeline, and then you get what we call an airlock, and it can the cross-sectional area of the flow is decreased because of the presence of air in it. I made this just to explain that further to you. I'm going to try and visualize it. Uh, if you have a pipeline like that, shaped like that. I don't know, exaggerating it like that. So if you have a pipeline like that, and uh, air rises, right? Unless you have a very high flow velocity, the air will get trapped over here. So if you got flow under normal conditions, you got flow. The water is flowing like that in that direction. So you got flow. Sort of delete that arrow again. Air will accumulate uh, in this pipeline. So the air will collect at that point, it will collect and collect like that. And you'll see as the air collects at that point, it's a high point, and if the velocity is not high enough, it will not push that air out. It will remain there at the top. So you then left with a very small cross-sectional area for flow. So you eventually throttling the flow like that at that point. And if the velocity is slow enough, you might end up actually with air down there, the air pocket sitting all like that. And if you got an air pocket like that, and the air pressure is high enough at that point over there, at that point in this air bubble, it could even stop the flow. You might not get any further flow occurring if it's enough to hold back the head of water at that particular point. That's what we generally would refer to that as an airlock. Yeah. So you don't want that's the reason you want to remove the air, and usually an air valve will be located at the high point. It's a special type of valve, and it'll be at that point, and it'll release the air from the system. The air valve it has polystyrene in it that floats in water that will float in water, but it's heavier than air. So it will release the air from the system, and once the air is released and now water starts coming through this valve, the polystyrene ball will sink and it will shut off flow. So it won't allow the release of water. It will only allow the release of air. Again, there's pictures on the internet, and you can look them up and read them how these valves work. And so an air release valve will usually be at a high point in a pipeline. Uh, how would air come into the system? Uh, there's many ways in which you can have air can accumulate in the system. The first is when you lay the pipeline, well, the pipe is actually full of air. You then introduce water into the pipeline when you open the valve. Then you need to remove the air from the pipeline, and that's where the air valves would come. You don't always have to release the air through an air valve. Sometimes just under normal operating in people's homes or things like that, from people's systems, those also will form uh, air release valves. Air can be removed from the pipeline from that point of view. But usually at a high point on the pipeline, uh, that's where you would find the location of an air release valve. uh, how would air come? The second way you can get air into a pipeline is you may have dissolved air in the water. Right, just remember where you have high pressure zones, and if for some reason there were air bubbles in the pipeline, they can go into solution because of the high pressure. And as the pressure lowers, usually as you're reaching a high point on your pipeline, the head in the pipe will be less. So you can then have, excuse me, uh, you can then have air being released, a little like shaking a Coke bottle, right? A cold drink bottle. When you open the cap, the pressure reduces, and then you get the release of air, dissolved air from that bottle, from the fluid in the bottle. And so that's how you could get it. Uh, another reason why you want to remove air from the pipeline is if you have pockets of air or air bubbles in the fluid that are flowing, uh, they, depending with the variation in pressure in the pipeline, with the flow at different parts of the pipeline, uh, when those air bubbles collapse, they literally, it's a sudden collapse of those air bubbles, and it introduces a shock into the pipe, and you can get cavitation on the walls of the pipeline when those air bubbles collapse. Right, so as the pressure, you get a sudden increase in pressure or decrease in pressure, those bubbles could collapse, and you would then get what we call cavitation. They can cause cavitation of the pumps, and it's cavitation is usually a serious problem when it comes to pumps, right? But it also does occur in pipelines occasionally. Okay, so that's what I've spoken to you about air valves. Read through all of this and you'll find it very interesting. There are some pictures here also where you'll see pictures of different types of valves and fittings. Uh, the picture at the bottom here that you see, a D, diagram D, that's a typical air valve chamber, air valve that you're seeing. The top there, you can see that's the air valve. So there's actually two air valves fitted on this particular pipeline over here. Right, you can see that there are two air valves that are fitted over there, and that's what they usually look like. That's what they, yeah. Then it will usually be it has to be, it'll either be exposed to the air, and then it can get vandalized or damaged, people passing by or whatever like that, or exposed to the elements, and sometimes it may get clogged or something. So it's usually inside a chamber, but the chamber has to be vented. It has to have a hole to allow for the release of the air. Right, so that's why you can see this one is within a chamber. It does not just within a chamber. The slab of the chamber, on the roof slab of the chamber, would require a small opening or hole for the air to be released, so the chamber itself doesn't become pressurized. And so that's a valve. Uh, the valve that you see here in diagram A, let me see if I can enlarge that picture. Uh, the valve that you see here in this particular picture here, this is what we refer to as a butterfly valve. It's a thin valve, right? It's a very thin valve, and it literally, just to illustrate to you how it operates, it's an isolation valve. It's to isolate the system. So that's what it is. It's an isolation valve. And if you have your pipeline like that, uh, then if that valve were open, what you literally see, it's a handle like that, and it's a plate, circular plate that's like the shape of the pipe like that. Right, so now it's open, it's parallel to the flow direction, so it will be open like that. If you were to close this thing, so if you had a handle here, so that's the handle you see in the picture there. If you turn the handle, then you turn it 90 degrees and it would then close up like that. So you'd see that circular plate. Now you look at it, it'll just be like that, and it shuts off flow in that particular pipeline. So that's a butterfly valve. A gate valve is very different. uh, for a gate valve, just if I may draw a diagram here for you, uh, you'll have your pipeline of that, and then that's the direction of flow. And in a gate valve, there's usually you'll see it's like a bubble at the bottom. It has like a bubble shape on the top like that. So it's a much larger uh, valve that you see like that, and you'll have the handle that would operate it. And in the gate valve, what you actually have in the pipe is like, sorry, I haven't drawn that nicely at all because I don't have space. Let me see how I can draw it. Okay. In the gate valve, it will have a big section like this over here, and like that. And inside it is actually like a gate, something. So that, and this goes up and down. When you turn the handle, you turn the lever at the bottom. This plate over here, I've drawn it wrong. It's actually perpendicular. It should be like that, and it's a gate like that. When it's open, it'll be in the up position like that, and when it's closed, then it'll shut off flow and it'll come into the bottom position like that. So you have a plate that moves up and down like that over there. Yeah, right. And there's all lots of other details that go with it over there, but it gives you the idea of how it operates. So that's how a gate valve operates. So it's like a sluice that moves up and down within the valve itself to open flow and cut off flow. Right. So these are just some typical pictures of valves. Uh, the, the, the what you see in diagram B, that's a typical scour valve, and you'll notice something. Let me just enlarge this picture so you can see it better. You'll notice looking at this picture. Now, I need to get it to the middle of the screen. This thing doesn't pan. Can you see it? Okay, right. You should see it now. You notice that the scour valve. Notice its position. It's not coming out from the center of the pipe like that. You have a T piece, but it's teed off from the bottom of that pipeline. Right, so it's teed off from the bottom of the pipeline. So that's it's called a scour tee. And that is because you want to remove the grit from the pipeline. It would be at the bottom end of the pipeline, or you want to drain the pipeline. If this T piece were at the middle of the pipeline, then you would not be able to drain the bottom half of the pipeline. So it has to come out from the lowest part of the pipeline. So from the bottom part of the pipeline, that's where it tees in. Just to, again, if I may draw a diagram to clarify that, if you have, for example, if that's your pipeline, uh, you would not, the normal T piece would come out like that. You'd have a T piece for the pipeline. So, but you cannot do that because then that water in the pipeline will never ever come out from the pipeline. So we cannot do that. For the scour tee, normally there's a special type of tee that it tees off from the bottom like that. You have a piece like that, and then you attach the valve at that point like that, and you can drain the water out from that pipeline. So it's always at the lowest part of the. It's a special fitting. We refer to it as a scour tee, and that's there. The symbol for a valve. That's something I haven't explained to you. That's in a pipeline system. We generally this is the symbol that you see in a pipeline. So you have your pipeline like that. the pipeline. And this particular symbol that you're looking at now, that's a symbol that represents a valve. So if you have a line diagram for your pipeline, you would represent it a valve with that symbol over there. The symbol will never be to scale in most circumstances, most situations. It's never ever to scale, but it just is symbolic to tell you that there is a valve at that particular position. Now, the skull valve that you see here in this particular one, this is a gate valve. That you can see that box over there, and if you visualize it, there's like a gate. That's why it's referred to. I'm coloring it in blue like that. So at the moment, there's no flow coming out, so the gate would shut off the flow in that pipeline. So that will be the position of that gate. When you turn the valve, when you turn the handle, then it slowly screws it upwards. The spindle, sometimes the spindle also rises. You also get non-rising spindle valves. The gate would then move to the top position like that, where I've colored it now, and then you can get flow through the valve like that over there. Right, so that's why it's referred to as a gate valve. You have like a gate in it or a sluice in it that you operate with the handle and that goes up and down. But you cannot see it because it's inside. The mechanism is inside the valve. Right, so that's on valves. Let me just go back to the picture. So these are some pictures just to illustrate to you the different types of valves that we have. I spoke about air valves. Scour valves, I've spoken to you about that. They're used to drain pipes, right, for maintenance. Sorry, I highlighted the whole thing. I shouldn't have done that. It's unhighlighted again. Okay, now something's gone wrong here. My apologies for that. Just trying to undo this, what I've done. Just bear with me. I'm just trying to. Okay, that doesn't matter. For the scour valves, they're usually for maintenance purposes, and like I said, to after a repair, to remove any sand or grit that may have been left behind in the pipeline, and also if any contaminants were introduced into the pipeline, to remove the contaminated water so that the water that's left in the pipeline is this clean potable water. That you can see, scour valves should be used to inspect clean of plant material and debris and tested over there. Right. Non-return valves, these will only allow flow in a particular direction. Uh, it's where you do not want flow in a certain direction. You only want it to happen in that in one particular direction. And it's part of the reason why you would use a non-return or why you want to control the flow like that is sometimes you would want to prevent the water from a pipeline from emptying out because it may develop a vacuum in it. You may not have an air release valve or vacuum release valve in a particular section of the pipeline, and then you would want to prevent it from emptying out. So the water that's in it must remain in it. So that would be one of the reasons that you would provide it a non-return valves. Right? So where you only want flow to occur, or sometimes you only want flow to occur in a certain direction, you would install a non-return valve. Non-return valves are commonly used in pump stations where you have a pump. If you pump, you're generally pumping upwards, you're not pumping downwards. Let me just draw a diagram here. So if you have a pump at that point over there, and then you're going to pump the water up like that. Right? You wouldn't pump downwards because then you can get gravity flow. So why would you use a pump? So while the pump is operating, it's the water is flowing upwards. But if the pump were to switch off, like load shedding or for normal, it's reached. You've pumped enough for the day and now it needs to pump off, then you have this column of water that's sitting there and you can get backflow occurring to the pump. It'll then backflow through the pump and may empty out into your pump station or whatever. So in those circumstances, we normally will put a non-return valve, and usually the symbol for that, it looks like the pipe is being pinched. You see just that one, that kind of symbol that you have there. So that's to stop. So the water can only flow in that direction, but it cannot flow back in that direction. So usually in a pump station, that's where you would commonly find non-return valves. That so that we spoke about that. Control valves, like I said, they could be used for the control of the pressure. Let's get this set. So control of pressure in the pipeline. Uh, you may also want to control the amount of flow in a particular pipeline, or you want to control, for example, the level in a reservoir. So it would have a specialized application. The different types of control valves are they listed here. Let me just delete all the clutter so it's easier for you to see that. Uh, you can see pressure reducing valves, pressure sustaining valves, so you want to maintain a constant pressure in the system. Then you get flow control valves that control the flow rate in a particular pipeline. You might want to have a constant flow rate. Level control valves, that's usually when you have reservoirs. Surge control valves, these are to prevent water hammer in your pipeline, and we'll talk about that when we do the section on water hammer. And then pump control valves also that we have over there. Right. Then you have the last section that you type of valve that, not a valve, but what we refer to as fire hydrants, and I'm sure you're all familiar with that, so that wouldn't need any further clarification. That's in the event of a fire, uh, where your fire engine would come up and they would connect the fire engine. It would flow into the fire engine tank. The fire engine usually has a pump in it, and they can then pump. In the event of a fire, you need large volumes of water. Like the normal uh, flow of water to a household, for example, would not be adequate to put out a large fire. But so you need larger volumes of water, and that's where we have fire hydrants that connect up to the fire to your fire engine, where there's a pump installed and is then able to pump the water under high pressure. So the reach of the spray can also be quite far. So if you have a multi-story building, even from the ground level, they may be able to spray water a few stories high to reach the fire. And so that's the need for fire hydrants. Break pressure tanks, these are specialized structures. You will not come across them commonly. They're usually used in bulk water supply schemes. And again, the name suggests, tells it all. It's basically a pressure reducing tank. That's not a valve this time. It's a tank that's used to reduce the pressure in a particular pipeline. And if you reduce the pressure in the pipeline, you'll get less wastage of water through leaks. You can also use a more economical pipe. It will require a thinner wall diameter if the pressure is reduced in the pipeline. How do these break pressure tanks work? Let me just explain it with the aid of a diagram. For example, let's say you have a reservoir at that particular point. So you have a reservoir full of water, and you then, let's say, you're now supplying a town or something in this particular town at this level of air. So you're supplying water here to that particular town, and the elevation of this particular town, for example, let's say if this is at 100-meter above sea level, that's 100-meter above sea level. Your reservoir might be sitting, for example, let's say at 400 meters above sea level, maybe at a very high point, because it may be serving other areas also. There may be intermediate towns or villages or something like that. In between, it may be serving. Now you have a pipeline that's coming, so that's serving this town, your main town, and from there you may be teeing off to those other smaller areas. The problem is that if you look at the difference in levels, you got 400. This is at a meter elevation of 400 meters, and the elevation of this town is at 100 meters. So the difference is 300 meters. 300 meters of head in that pipeline. That's an extremely high pressure to have in your system, 300 meters of head. And then you would require a very, very strong pipeline, especially as you nearer the town like that. So in those reaches, for example, somewhere in those areas there, you can have very, very high pressures in the town. So you can install uh, a pressure reducing valve if it's a small pipeline. But if you're supplying an entire town, it would could be quite expensive, and it may not be adequate enough to reduce the pressure to lower levels. So instead of 300 meters, ideally you may want to reduce the pressure to maybe about 60 meters or 50 meters of head. So how can you do that? How is that done? Uh, it's done by utilizing what we call brake pressure tanks. I'm deleting all the clutter here, and just to explain to you what happens in a brake pressure tank. So, or how a brake pressure tank works. Right. So you would supply water, for example, you'd build a pipeline of that, and let's say the pipeline. We now come to a head. Let's make this. Let's say this is now at 325 meters elevation. We have reached an elevation. So there's a 75-meter head difference at this point. At this point, we build, you can think of it like a reservoir, right? But its purpose is not really for storage of water. So we build a form of a reservoir, so like that. We have a reservoir like that. So the uh, water flows in into that reservoir. It's open to the air at that point on the top. It's open to the. It may have a roof slab too, so that the water is not contaminated. You don't get dust and dirt, But it's vented. They may have a small vent to allow air to enter or to leave the reservoir, and then so the water fills in maybe up to a certain height in this tank. We fill in up to that point, and then we attach another pipe like that, and we go, and then we might end up building another one down like that over there, and we have a series of these tanks like that. These are what we're referring to as brake, and then we supply the town. These are what we refer to as brake pressure tanks. Now, what is happening here? For example, the pressure in this particular pipeline over here at this point may be 75 meters of head. That's what we're talking of, 75 meters of head. At this point here, whatever the depth of the reservoir is, we might have maybe sitting with 5 meter of head at that particular point in that pipeline over there. In this pipeline over here, because this is exposed to the air again, right? So that 75-meter of head does not transfer across into this pipeline over here. It will again be, if that tank is 5 meters deep, the worst case is we might end up with 5 meter of pressure there, and then we come down and we may end up with 75 meters of head again at that point. And then so we do it like that through a series of these tanks. Again, we might end up worst case scenario 5. I'm saying worst case because if the tank is empty, or close to empty, or close to the outlet pipe, if the level of water in the tank is close to the level of the outlet pipe, then it will be almost zero, right, the head at that point. And you then have, let's say, a difference in elevation here of about 75 meters. So you'd have that. So you can see, instead of having a pressure in the pipeline at the town of 300 meters, we actually now will be sitting with a pressure at that point, and the head in the pressure in that pipeline of only 75 meters. Like that. So that's the purpose of a brake pressure tank. That's when you can see we're breaking the pressure in effect. We're taking advantage of the fact that the moment we have the water exposed to the atmosphere, like that, where the surface of water is exposed to the atmosphere, then the value at that point would be zero. That's what we're using and taking advantage of that particular point. Okay, so that's where brake pressure tanks are used, and if you note here also, it tells you essentially small reservoirs, and they're used to prevent excessive pressure in the distribution system on the downstream side. Uh, you can read through all the discussion on that and go to that about hydrants and brake pressure tanks, and that's all discussed. That's a diagram showing you, as mentioned earlier, about a marker. This is a hydrant marker, so you can see there's a box there, and that's a marker there. So there's the marker for the hydrant, and this will usually be the valve that controls that fire hydrant. Right? You can see there's a valve there. Uh, Other fittings, these are usually the municipality would install. They're not within. I'm not going to spend time on this within this module. Water meters. You may have water meters to individual stands, and you can also have bulk water meters to measure the amount of water in a pipeline. Now, why would one install bulk water meters? So bulk water meters, I'm referring to the water that's supplying a town. So let me just come back to this diagram. Uh, we might decide, for example, to install a meter at that point in that pipeline over there, because if you install a meter at that time, then it would give the water supply authority uh, an opportunity to measure the amount of total amount of water supplied to that town. Right. Uh, and for example, if we were teeing off here to another town like that, so they may put another meter, for example, at that particular point or at that particular point like that. Uh, Sometimes you may find meters installed like that. Uh, and the reason would be why you'd have a series of meters like that at the T intersection, like what I've shown, would be if you would be able to pick up if there are leaks in the system. Right, so you know that okay, how much of water is going off to this particular town here, uh, and how much of water is going down to that particular town. And if you're measuring it back to further down at the town again, if those 2 meters are not measuring the same amount, then you know there's a leak in the system. Right, so in a bulk supply system, it would be used to measure the bulk supply to to a town or a village, and also it would be used to detect leaks in the system, or to give you an idea of which portion of the pipeline has developed leaks in the system. Right, so that would be the function of water meters in the bulk supply system. Various meters, depending on how much of flow, whether they're meant for domestic purposes or whether they are for bulk pipelines, what they measure. Uh, for example, the one that you see on the right-hand side is capable of actually measuring, if you look at it, it's to 3 decimals. So 3 decimals would be to the nearest liter of water. Right? That would be to the nearest liter. And then again, you'll notice a further, sorry, I got it wrong. Sorry, I got it wrong. It would measure, some of these measure to the nearest milliliter of water, the last digit of here. It could be as accurate as that. So they could even pick up a teaspoon of water that you've used. Right, that's how accurate some of these meters are. So they're fairly accurate devices, and you'll notice the normal when the water meter when they come to read your water meter, they would not usually read these red ones because that's accurate to within a liter. Right, so that's within that 400 over there. That's to within a liter. That's would be uh, that's to within a liter. That's zero point 0.1 of a liter, and that's 0.001 of a liter. Like that. But depends on what on the supply, whether it's a bulk meter or not. A bulk meter would not need to read it so accurately. Uh, so different meters for different situations that you would have. Uh, these are just showing you typical fittings for bulk meters, for meters that meter installations, how they are done, and you can see the meter is at that position as indicated there. The reason why you have this, the meter needs to be read, so it will usually be above ground to facilitate reading of the meters, right? Uh, the section on chambers and markers, I'm not going to cover that. These are just to help on the ground to identify your pipes. So that's where markers. Chambers are used to house our valves and fittings, special fittings and valves. They would need some valves can go directly into the ground. Some of the gate valves, for example, they can be this. You can put them into the sand and whatever. But some valves they would require a chamber. So, for example, an air valve you cannot just cover it up in sand. It's not going to work. That's it needs a chamber for because it needs to release air. So you can read up on this section. It will just be of interest to you, but it's not required for this particular model. The section on thrust blocks, we'll study that in further detail later in this particular module. When you have a bend in the pipeline, then you have a change in momentum. Right? The direction of flow is changed, so that there's a change in momentum, and there will be a force in the pipeline. So, for example, if you have the pipeline takes a bend like that, then you're going to now you've changed the direction of flow. It would require a force to change the direction of flow, and for every action there's an equal reaction. So this pipe would want to move outwards like that, and we would need to build a thrust block. So the thrust block would help to hold or keep that pipe in place or anchor the pipeline as at that particular point as it changes the direction of flow. And the special designs that apply to this, we normally will read it off from a table, and you to size those particular thrust blocks. You can see examples of them given here. You can see that's a thrust block there, that's a thrust block, depending on different situations. So, for example, you have an T intersection, you have flow at that point. Obviously, it's going to apply a force on this pipe over here. It's going to push the pipe out. So that's why a concrete thrust block is usually constructed on the back of that to support the pipeline and hold it in place so that it can overcome the thrust from the flow that's joining into that pipeline. Read through this. It's again all you'll find it interesting to read through all of this. Uh, right, so that's this whole chapter or chapter 7 on this particular section. The section on reservoirs, we will study distribution reservoirs later in this module also. You'll learn to size them. We'll come back to that. But what you see in this particular chapter, that's for you should study what's in this chapter, all the sections that I've spoken about. Okay, so I'll stop the lecture at this point just to remind you again, your test on Monday at 8 o'clock. Right, it will be online. Right, and I'll send you further communication. Well, I don't need to send you further communication on that. Right, so it will be on Moodle. Right, if it's online, you are third-year students, so you'll be familiar with using Moodle and doing conducting online tests. Right, so you're Monday 8 o'clock, and the scope of it, all the sections before the Hardy Cross section. Right, whatever work we've covered before Hardy Cross, the Hardy Cross method, all of that will be within the scope of the first test. Any queries before we end the lecture?
So where can we find this note?
Okay, immediately now when I end the lecture, I'll post the link for you for that on the Moodle site. In fact, I'll put the book for you because it's available for free download from the Water Research Commission. If you go to the Water Research Commission website, to actually find it on their website, they have hundreds of documents, thousands of documents. Yes, it's not that easy to find it. So I'll post the link for it, and I'll post the document for you on the Moodle webpage for that. Right? And I'll also post the updated, the corrected tutorial memo that I went through earlier.
So, sir,
Yes, go ahead.
there will be also theory
What you'll be also
regarding the test.
theory.
Yeah.
Yes, you can expect some theory, but if it's an online assessment, just to make something clear, if it's online, the theory is not going to be a direct way you just copy a line from your notes or something like that. Then it's defeating the purpose. So if there is theory, it will be something that you would have to explain, maybe the difference between this or that or something that you would not find the answer in a book or in your notes. Right? Yeah, but you can expect theory, yes.
All right.
Anybody else? Any other queries?
So with this chapter, yeah, must we focus on the valves, water meters and stuff? Not everything.
The valves, not even the. I just discussed the water meters,
Just the valve.
but the main is the valves that's our main interest in the network. The context of water meter would this be, for example, in a bulk water supply system, where you can use the valve, the water meter so you could pick up if there are leaks in the system. And by comparing the valve readings at different points, or so not valve, the meter readings at different points in the network, you'll be able to pick up that whether there's to pick up water losses in the system. Does that answer your question? But it's not within the scope of this particular module. Don't worry about that. Anybody else? Anybody? Okay. There's no further queries. I can end the lecture.
So,
Yes, go ahead. I'm listening.
so you said in the email that you have to have access to a printer for the test.